In this video, we'll begin our last chapter. Chapter 11 does a lot more than just sequences. There's ideas of sequence, series, and if you go far enough, they eventually start talking about probability. But we're just going to take a very basic look at these ideas, so we will only look at the sequence parts of any of these sections. So this is a little similar to Chapter 10. There's a lot more we could say about conic sections. We could look more at applications. We can get deeper in looking at foci and asking other questions about length of major and minor axis and all kinds of other stuff. But again, we're taking it very basic there. The idea, be able to have an equation and draw the correct conic section with the appropriate information, or vice versa if I give you the sketch to be able to get the equation. Well, you'll see we're going to do very similar things here as well. So first things first, we're going to start with the idea of just an introduction to sequences, and then you'll see 11.2 and 11.3 we'll go through very quickly. There's really just one key idea from each of these that we have to discuss. So first thing, the introduction to a sequence. We use a lot of different notation for sequences, and we very commonly use lowercase letters, kind of like how we use f of x, g of x, h of x for different functions. Well, we tend to use things like a sub n, b sub n, c sub n as the general terms for different sequences. But before I get too far into the notation, just first things first, how about a quick definition of what is a sequence? A sequence is an ordered list of elements. Now, technically speaking, this idea of elements, this could be anything. This could be symbols, this could be notation, this could be letters, but for our purposes, we'll only be looking at sequences with numbers. So, the second part is to realize this is an ordered list. So now I'm going to jump right in and give you a couple of sequences. If a sub n is the sequence that goes 1, 2, 3, 4, 5, comma, dot, 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 sequences can end at a certain point, but a lot of times we like to think of this as an infinite sequence. This can go on forever. And then in this first one, I'm being very clear with my terms that if a sub n is the general sequence, well, I could use subscripts for each individual term. That the first term we'd call a sub 1, the second term a sub 2, then a sub 3, then a sub 4, and so on. That we could say generically for any, this would be a sub 5, and I keep going on. So I could keep that idea, and this is just a coincidence that the subscript happens to match the number. But I'm trying to point again to the fact that this is ordered, that we should be able to look at a sequence and say, what is the fourth number in that sequence? Again, technically fourth element, but again, the fourth number. What is the first number? What is the 10th number? What is the 1022nd number? And the order makes a difference. Because if I had b sub n, and b sub n went 5, comma 4, comma 3, comma 2, comma 1, comma dot, 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 well, hopefully, as we get some practice, part of the idea of sequences is just learning patterns. So that if we just see several of the terms and we see this dot, 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 that we could continue. So that naturally this sequence would continue 6, 7, 8, 9, and so on. But this one would continue 0, -1, -2, -3. That would be the pattern that we would be seeing here. But my point for right now is that a sub n does not equal b sub n. If you just purely looked at the numbers, and for those who are familiar with sets, the sets 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1 are the same. But as sequences, it's not just having the same elements. It's not just having the same values. It's having the exact same values in the exact same spots. So here the first term was 1. Here the first term, well, this would be b sub 1. But a sub 1 does not match up for b sub 1. So again, just because eventually I will get a 1 here, and eventually I will get a 5 here, that doesn't matter. They have to match at every single spot. So that is our, again, a lot of our basics of sequence notation. just looking at a sequence, having a bunch of terms given, understanding, being able to find some patterns. But now let's realize that while this certainly can happen, we're just given a bunch of terms. The kind of the more ideal situation would be, let's have a general formula. So if I told you C sub n is, for this first one, let's go n squared divided by n plus 3. That if I gave you that general formula, and now I asked you for any of the terms, well here, either the terms are already given. If I say, what's A4, the answer is 4. What's B4, the answer is 2. But even if you go past, you at least have a way to get to see a pattern. And if I said, what's the 7th term in A? Well, keep going. The 6th term would be 6, the 7th term would be 7. What's the 7th term in B? Well, I'd have to keep going. The 6th term would be 0, the 7th term would be -1. But the more ideal situation would be, here's a general formula. So if I said find the 7th term of the sequence C, that's literally saying find C sub 7, and just because this is a subscript, we're still replacing the n on this side. That's just notation. But on the other side, just treat this just like an f of x. If I told you f of x was x squared minus 3, and I said find f of 1, you'd plug the 1 in and do the work, and you get -2. So what happens when you plug the 7 in for n? You do the same thing. You get 7 squared over 7 plus 3, and you get 49 over 10. And that's a fine answer. Maybe you'd rather look at it as 4.9, but that's the idea. So just through these first three, we've got a lot of notation, but we also started to realize this kind of ideal situation, that this is the general formula. And that the general formula, just like the general formula for a function, is often better than just having a bunch of the terms. So even if we have a bunch of the terms, you'll see that there's a lot of problems in the book that talk about trying to then move and get the general formula. Because with the general formula, well, you want the 7th term, you plug in 7. You want the 10th term, you plug in 10. You want the first term, you plug in 1. I mean, here, both of these gave you the first 5 terms for sequence A and sequence B. What if I told you to find the first 5 terms for C? Well, you would just do this idea. You'd find C1, you'd find C2, you'd find C3, you'd find C4, you'd find C5. And you could leave it in that notation, C1, plug it in, 1 squared over 1 plus 3, you get 1/4. 2 squared over 2 plus 3, you get 4/5. 3 squared over 3 plus 3, you get 9 over 6, which can reduce 1.5, 3 over 2. So again, this is all fine. 16 over 7, 25 over 8. And to just leave it in that form, clearly see each value, and by including the subscript, it's clear. That's the first term. This is the second. This is the third. You could also just write them in order, ignore the C1, C2, and just put them in order. The same way these 5 terms up here were in order. So that would also be fine. Either way, that would be a perfectly good way to answer this. But once again, it's certainly nice that we had the general formula there for us. Still moving along. So again, book talks a lot about this, gives you a bunch of standard formulas, a general formula, and asks you different questions about finding different terms. Find the 10th term, find the first term, find the first 5 terms. So we see a lot of that. And there's 2 big things we have to finish. Again, everybody, remember, this is a general introduction. There's plenty of other things. Other people have seen little pieces of this before. Maybe you know a little more. If you read deeply into the sections, they'll go beyond just the sequences and talk about the series, talk about adding the terms in a sequence together. And what's the sum of those series? Well, how far do you go? So there's a lot of other information in the book. Again, we're really trying to stick to some concrete basics. And we really just have a few remaining ideas from 11.1. The next thing I have to show you is this concept, which is a factorial. Generically, I'm writing n factorial. And again, some of you may already be familiar with this. So let's just see how factorials work. Factorials come up a lot in sequence problems. Some of you will eventually get into Calc 2, and that all these facts are just very readily used when you get in Calc 2. You'll get a lot more of the series information, but just a lot of the basics of notation. And again, factorials come up a lot. So the idea generically of n factorial is that you multiply the number n times n minus 1 times n minus 2, and you just keep subtracting 1 and multiplying until you get down to the number 1. So this only makes sense if you're applying this idea to whole numbers, positive whole numbers. If you did this with negative numbers and kept subtracting, this would go on forever. Same thing with any fractional or decimal values. But if I told you to find 5 factorial, well, that would be 5 times 5 minus 1 times 5 minus 2. And again, I just keep going down until I get to 1. And you could do this on your calculator. If you look, some of you can find there are factorial buttons, different calculators, they're in different spots. I'm not worried about that because we're not going to do that much with them. And the little bit we do, it'll be easy enough to do the arithmetic by hand. So this, if we grind it out, well, 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120. But now realize, now that I know 1 factorial, how I can use that to help me in other situations. That if I wanted next 6 factorial, well, true, by definition, 6 times 5 times 4 times 3 times 2 times 1. But notice what that boils down to. We already did all of this. All of this is 5 factorial. So one way to find 6 factorial, well, you can start from scratch, but if you already know 5 factorial, just do 6 times 5 factorial, and there's your next factorial. Notice these numbers are getting big in a hurry. If I keep doing this, 7 factorial will be 7 times this. That's 5,040. 8 factorial will be 8 times that. That's 40,320. 9 factorial, you're already at 360,000. 10 factorial, you're over 3.6 million. You start using a calculator, you get into the 20 factorials, you need scientific notation. They get to be very, very large numbers. So, what I want to do here is point out the nice ways you could break these down. So that if you had something like 8 factorial, well, just to point out, it's not just this. It's not just 8 times 7 factorial. You could keep counting down and at any point stop and say factorial. I can go 8 times 7 times 6 factorial. Or keep going, times 5 factorial, times 4 times 3. At any point, I could just stop and say factorial because that'll cover everything else. So now, getting into the second page here, let's see how we can simplify these expressions. So if I asked you to do, and let's start easy here, if I wanted 5 factorial divided by 3 factorial, well, we can do all the work for each one and literally get 120 divided by 6 to get a final answer of 20. But if we just get to here, we could realize, hey, this is all multiplication and lots of stuff cancels. So all that's really left here was 5 times 4, a quicker way to get 20. And look how that gets, as these numbers, as I give you bigger ones, well, this wasn't terrible to do all the work, but in my next one, what if I wanted you to do 11 factorial divided by 8 factorial? Well, again, calculators can still handle these. You do get error messages because even with scientific notation, I believe it's something like 27 factorial, you've already overloaded the calculator. But here, so you could plug this in, but take advantage. This is the smaller one, so expand this factorial until you get to this one. So this will be 11 times 10 times 9 times 8 factorial. I keep going down, but I'll stop at the 8 factorial because that cancels here and here. I'm not just canceling the 8s. The factorial shows that I'm canceling everything below. I'm canceling the 7s, the 6s, the 5s, the 4s, and so on. So now all that's left is 11 times 10 times 9, which is 990. Okay, one more like this. Again, factorials do get used in a lot of different places. You can do these things generically. It's not even just with numbers. If you had something like n plus 3 quantity factorial divided by n plus 1 factorial, well, this is n plus 3 times n plus 2 times n plus 1. Hey, that matches. Stop expanding. Don't keep going times n minus 1 times n minus 2. Stop expanding. Put the factorial. And now we can't do any better. Maybe we want to FOIL this out, but you'd probably just be leaving that as n plus 3 times n plus 2. But one more with numbers. Let's finish up. This is going to look a little ugly at first. And again, with calculators, if we only use the calculator, we would not be able to solve this. So let's look at 53 factorial divided by 51 factorial. If we're getting the hang of this, just expand. I'm intentionally leaving the bigger one on top. Practically speaking, in other situations, that is what happens. But it's just expand the bigger one until you get to the smaller. So 53 factorial would expand to 53 times 52 times 51. Hey, it matches. Stop there. 51 factorial to cancel with 51 factorial. And I will still use my calculator to finish this. And all I'm doing to finish is just 53 times 52 to get 2756. So again, you'll notice a few problems just trying to get you to work to evaluate and simplify a few factorials. There's one or two problems with the sequences. They put this type of factorial notation in a general formula. So again, just to get you some practice plugging in and getting those values. So the last two things to finish up with this general introduction. I started off showing you the letters. And this is such a common way to introduce a general sequence. Just like with functions, everyone. Why do we not just always use f of x? Why do we use g and h? Well, we might have more than one function, and we need to be clear which function we're referring to. Well, the same thing happens with sequences. So why do we use a and b and c? Just again, to be clear, I say find the 7th term of a, you're up here. I say find the 7th term of c, you're down here. To be very clear so we know which sequence the question is referring to. But sometimes you will see sequences that don't use those exact letters. They use some curly bracket notation. Now, curly brackets in general are used for set notation. But if you add a little extra component, if you do curly bracket n squared over n plus 3, n equals 1 to infinity. That may not look like it, but that's the same thing that we had for c sub n a few minutes ago. That all you can do inside of these curly brackets, you can use the general form, but the way to make this clear that this is not just a set of numbers is this extra notation at the end. That you're kind of introducing a counting variable. That n is your counting variable, and that you're starting with n equals 1. Doesn't that make sense? Isn't that the most natural place to start? Start with the first term, then the second, then the third. So that's why we're starting with n equals 1, and we can go forever. We can stop this after 5 terms. If I said n equals 1 to 5, then it would just be the first 5 terms of that sequence. So again, just a little bit of notation. Sometimes it seems strange, but there are times people don't want to start with n equals 1. So that's fine. If you say start with n equals 2, well, you would just write that here. And the first term would start with n equals 2. And then the second term would have n equals 3. It seems a little weird, but that can come up. That might be something that would be necessary to be done. So that's just a quick thing to mention. And the last quick idea, these sequences that I'm giving you up here, they're nice sequences. There's nothing special. There's no formal name. But once we start seeing a pattern, we can use that pattern to move along. But even better, this general formula, I could jump to any term at all that I want. But there is another special type of sequence that we should have at least heard this word before. For people who have interest in computer science, you've probably heard this before. There is this idea of a recursive sequence, right? This idea of recursion. This is kind of like setting up some sort of like I need previous information to tell me later information. So before I give you a full definition, let's take a look at a recursive sequence. If I had something like this, I wanted to write out a bunch of terms. This is not just a random sequence, everybody. This is a very special sequence. It has its own special name. I'll talk about that in just a moment. But just, can you notice what pattern is going on here? It's certainly not obvious. I mean, these first couple that I was just going up by 1 or going down by 1, that was nice. If you start looking at these terms, the pattern is not as obvious, especially because some of them, they kind of, I don't know how to say it exactly, but it's just like, looking up here, some of these could have reduced. That's what I meant to say, I'm sorry. That if I reduce this, I would lose my pattern, but without reducing, just looking across the top, hey, I just notice all of them are perfect squares, and that's 1 squared, 2 squared, 3 squared. So I could start to predict that this next one would have a 36 on the top, then a 49 on top. Well, what about the denominator? Well, I didn't start at 1, but I still just keep bumping my denominator up by 1. So that even without this formula, that maybe I can predict that my next term would have been 36 over 9. And then my next term would have been 49 over 10. So again, just to see, the idea of patterns is always there. But now coming back to this one, do we see the pattern? The pattern is you're taking the previous 2 terms and adding them together to get the next. So that 1 plus 1 gives me 2. But then 1 plus 2 gives me 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. 8 plus 13 gives me 21. 13 plus 21 gives me 34. Can you see what the next 2 terms would be? 21 plus 34 would give you 55. And then 55 plus 34 would give you 89. So this is just one example. Specifically, if you have not heard of this one before or seen this before, this is the Fibonacci sequence. Fibonacci was an Italian mathematician. He noticed a lot of these patterns in different areas of nature. Specifically, he was looking at breeding patterns for rabbits and just noticed some of these combinations. So there was a lot of interesting other aspects and connections. But again, I just wanted to show you that as one quick example for a recursive sequence. And these are tough for everyone because you can't just jump and say, give me the 20th term, give me the 30th term. In my normal sequences, I can do that. If I've got a general formula, you want the 100th term, plug in 100. But in this idea, you want the 100th term, well, you need the 99 and the 98 terms. But if you need the 99 term, you need the 98 and the 97 term. And if you need the 97 term, you need the 96 and the 95 terms. And I would play that game and go all the way back, that for me to get any of the later terms, I need every single previous of the previous terms. So again, they come up, They're used a lot in computer programming. There's a lot of other little situations, but I just wanted you to see that briefly. How would you write a general term for this? I'd have to do something like this. Let me just make up a new one. So not just the Fibonacci. Let's look at one last recursive. So let's say you are given D1 equals 4 and D2 equals 10, and that D sub n is equal to D sub n minus 1 plus 2 times D sub n minus 2. That formula may look a little similar to this, but to realize C sub n was only on one side and everything else on the other was just plain n's. Here these n's are more subscripts. So the way this formula would work, I'd realize I already have the first two terms. So if I want more terms, let's specifically, let's find D3, D4, and D5. So that in total we'll have the first 5 terms. So I've got 4 is the first, 10 is the second. Well, now to get D sub 3, I'd still plug the 3 in for n, but notice how this works. When I plug in 3 for n minus 1 is a subscript, so I get D sub 2. And then similar, I plug 3 in for n, I get 3 minus 2, I get 1 as my new subscript. So this is telling me, take the second term 10 plus 2 times the first term 4, and I'll get the third term is 18. And then I keep going. D4 would be D3 plus 2D2. How do I get the fourth term? I take the third term plus 2 times the second term. And I'd end up with 38. And now some people, they can eventually start to realize what's happening here, that this is telling me take the term before it plus 2 times the term before that. So just one more to finish D5 without following the formula. Just realize I'll take the term before it plus 2 times this one. So I'll end up with 36 plus 38 would be 74.